Assalamu alaikum warahmatullahi wabarakatuh, and welcome everyone to the lecture, part 3 of chapter 7 about activated sludge system. So in this part we will focus on two main modifications. The first one is extended aeration. So what is extended aeration? The extended aeration process is one of the modifications of the conventional activated sludge, and this is basically applied for the low flow areas, like if we want to construct a prefabricated plant for a school or for a small premise or university, for example, or maybe for small industry, which is sometimes or mainly lower than 3000 meter cubic per day. So extended aeration system is more suitable to apply, and now we will know why. Okay, this system is complete mix system and provides biological treatment for the removal of biodegradable organic wastes under aerobic conditions. Almost same as conventional activated sludge, but there are some differences. As we said just now, this is popular in treating small flows like schools, trailer parks, villages, and which has low BOD loading. Okay, this is one of the conditions. So it has to be a small flow and low BOD loading. And the continuous complete mixing is applied by diffused air or mechanical mixers, and the aeration process or the aeration period is longer than the conventional activated sludge. Okay, 24 to 36 hours. And here, because the flow is small and the BOD is low, so we apply aeration periods, which is longer periods, and this will result in the excluding of primary treatment stage. Why? Because there is low amount or small amount of sludge compared to the conventional or high flow treatment plants. So there is no need to apply a primary treatment stage. Okay, so this system is a modified system of the conventional activated sludge. We apply the extended aeration, which means that it is a more aeration. Extended means we extend the period of aeration, uh, and the flow is smaller. Is lower in lower rates, and the BOD is quite lower, and the sludge amounts are also lower. So the more economic is to apply extended aeration instead of conventional aeration. This will cut the cost of sludge handling, because if we exclude primary treatment stage, so the sludge wasted and sludge handled is also lower. Okay, is less than the conventional activated sludge. So this is basically for treating small flows, which comes maybe from a school, from parks, small parks or small premises, and so on. This is a schematic diagram of the extended aeration system. The main difference compared to the conventional activated sludge system is that there is no primary treatment. As you can see here, we put a raw sewage, which comes after the preliminary stage. Of course, we will apply the screening coarse screens, fine screens, grit chambers, and oil and grease removal. These are basic, which is applied for any, or should be applied for any treatment system. Okay, and then we send the wastewater will be sent directly to the aeration compartment. Okay, as I said in the previous slide, there is no need for a primary clarifier because the sludge is, the sludge amount is low. Sludge amount is low. Okay, now here are some pros and cons for the system. First, the pros: it is better at handling organic loading and flow fluctuations. Why? Because there is a greater detention time for the nutrients to be assimilated by the microbes. Okay, so there is a greater retention time, so handling the organic loading and flow fluctuations is better. And second, it is odor and nuisance free, so it has a relatively small footprint, and mainly or generally the system can be landscaped and match the surrounding area. Okay, because it has no odor. For the long lasting or aged, we call it aged sludge. Okay, so the sludge becomes without odor. And finally, it does not require a primary clarifier, as I said before, because of the low sludge yield. Okay, low sludge yield. For the cons, first, we can't achieve denitrification without additional unit process. Okay, longer aeration period, and hence we require more energy. Oh yeah, and the flexibility is limited to adapt to changing effluent requirements, and these effluent requirements can be maybe resulting from regulatory changes. So the flexibility is limited because the system is small. And it's not fabricated with for to be extended or to be expanded. Okay, so it is fabricated only for a small premise, or we call it prefabricated for a small premise or for a small area. Okay, those are the main pros and cons. And the design and operational parameters, as we can see here, is quite different from the conventional activated sludge. First, the FM ratio. FM ratio is lower compared to the conventional activated sludge, and here we allow, or it is allowed for the microbes to grow slowly, and that makes the detention time also, or the hydraulic retention time is quite higher. Okay, and sometimes goes more than 24 hours. And sludge retention time, this is the time of sludge spent in the aeration tank. Okay, it's from 20 to 30 days, which is higher than the conventional one. Volumetric loading, mix leaker concentration, also not so high. Recycle ratio is very high because the sludge amount is low. The sludge amount is very low, so we need to make recycle ratio higher than the conventional one. Okay, and the air supply also is higher, and that's why extended aeration sometimes it needs more energy to apply, but this is okay because we are only using it for a small premise, so the size of the plant is generally smaller than the conventional plants. Here's an example. An extended aeration sewage treatment plant treats 1,500 meter cubic of sewage daily with a BOD concentration of 300. So we have to calculate the volume and check the hydraulic retention time if we want to apply for extended aeration. Okay, and determine the quantity of sludge wasted per day. We assume MLSS of 3,500 and solid retention time of 25 days. So here's the solution. First, we have to choose F over M ratio, which is compatible, within the range of the extended aeration. So we choose it as 0.1 kilogram BOD per kilogram of mixed liquor suspended solids day. So using the equation of F over M, we can find the value of V. And don't forget to substitute the X in thousands. So this is, in kilogram. This is 3.5, which is 3,500 converted to 3.5. Also the S node, the S is 300 firstly, so we apply it as, or we substitute it as 0.3. Okay, the Q is 1,500. The F over M ratio is 0.1, so we can find the V. V is 1,286 meter cubic. Then we have to check the HRT. HRT equals V over Q. V over Q and times 24 to find it in hours. So we have 20.6 hours, which is okay, between 18 and 24 hours. Now let's check the volumetric loading. So volumetric loading equals Q times S node over V. So the result will be 0.35 kilogram BOD per meter cubic, which is okay for the, according to the parameters or design parameters ranges for the extended aeration system. Here we calculate the quantity of sludge wasted per day. So using this equation, SRT equals Vx over QWxu, we can see that QWxu is actually the amount of sludge wasted per day, because QW is the flow of wasted sludge, and XU is the concentration of mixed liquor suspended solids in the wasted sludge. So QWXU is the quantity of sludge wasted per day equals Vx over SRT 1,286 times 3.5 x over 25. 25 is the SRT, so equals 180 kilogram per day. So this is the amount of sludge wasted per day. You can see it's a low amount compared to any conventional activated sludge system. Okay, now we talk about something we call oxidation ditch. Oxidation ditch. As you can see in the figure, this is a plan view of the oxidation ditch. Actually, the oxidation ditch is a particular type of extended aeration process, and the aeration tank is constructed in a ditch shape, on an oval shape, as you can see in the figure. The aeration tank consists of a ring-shaped channel. As you can see, ring-shaped channel is normally from 1 to 1.5 meter deep, and the cross section of the channel is sometimes trapezoidal or maybe rectangular channel. Anyway, as you can see, we have two aeration rotors or two aeration points in the channel. These will provide the aeration in two stages of the channel. So for example, if this is the influent point and the flow will start this way, okay, will move this way. So at this point there is an aeration, so we expect that the wastewater in this zone moving this way is in an aerobic condition. Okay, aerobic condition. So there's efficient or sufficient amount of oxygen. So by moving and before reaching this point, the oxygen amount is getting lower. So we apply another aeration rotor to increase the amount of oxygen required, so that we can maintain the oxygen required throughout the ditch. Okay, and the cycle continues. So this system can be operated either as a fill and draw system, which is batch system, or can be also applied as a continuous system. It depends on the on the configuration and on the design of the system. And of course, the excess sludge generated is wasted through a waste pipeline, and the effluent is moved out from the ditch this way to disposal or to a tertiary treatment. So this is basically only a modification of the extended aeration, so it's not considered as a general or major modification of the conventional systems. Now we will move to the last modification, which is the sequencing batch reactors, SBR. So the SBR is a kind of fill and draw activated sludge system. So this one is a batch operated system. It's not a continuous system. And in this system, the wastewater is added to a single batch reactor, as we said, and then discharged. Okay. Equalization, aeration, and clarification, which is the sedimentation, they are all achieved in a single batch reactor. So all the processes, the aeration, the sedimentation of sludge is all achieved in one compartment, in one unit. Okay. As we know, in the conventional system, this has to be separated into two tanks or two units, the aeration tank and the clarification. But in SBRs, we will achieve all the processes in one system. I mean, in one compartment or one unit. As you can see here, we have one compartment, but following different operating phases. So the first phase is the fill or filling phase. Here, where wastewater enters the reactor and fill the compartment, and then aeration started, and the reaction of the mixed wastewater will start, and this depends on the effluent quality required. Reaction time depends on the effluent quality which is required. And the third stage will be the settle. Okay, here the biomass will be separated from the final effluent. Okay, as you can see, it is the same compartment, but we stop mixing, so we allow the wastewater to be separated, or we allow the sludge to be settled, and then decantation or drawing the wastewater out of the tank. Okay, and this will be after the sludge is settled. Okay, and finally there is a final stage or final phase, which is the idle. This is a time between decanting and filling. Okay, it ranges between 0 to a few days sometimes. It depends on the wastewater flow or the design of the wastewater system. So as you can see here, we have only one compartment, and I mean one unit, one tank, and all the phases are achieved through this tank. So again, this is a configuration of the conventional activated sludge system, which we only use one unit to achieve the treatment target. Okay, now in order to achieve the performance of the system, we normally apply 2, 3 or more of batch reactors or batch cycles. Okay, so when one cycle is reacting, the other unit or the other cycle is filling, and when the second cycle is filling and reacting, the first one is still in the drawing phase, so the third one will start to fill. So in that case, we can use 3, maybe 4, maybe 5. It depends on the wastewater flow, and those can be controlled together using what we know as the PLCs. Okay, so one unit operates when it closed, the wastewater will be flowed to the second one. When it is closed, the wastewater will be flowed to the third one, and so on. until the last one is operating or finished, so the first one is ready again, so it will receive the wastewater again, and so on. Okay, so of course it is successfully used for treating both municipal and industrial wastewater. Okay, and they are uniquely suited for low or intermittent flow conditions. Here are some advantages and disadvantages of the system. Basically, the system requires less space, of course, because we are using only one tank instead of two. Okay, the operating flexibility and control. It is flexible to operate according to the requirement. We can increase the time of the operation, so we can achieve higher quality of treatment. And finally, the capital cost, of course, we can achieve high saving of capital cost because we are eliminating clarifiers and other equipment. The disadvantages, mainly the higher level of sophistication. Okay, timing units and automated controls between the different phases and the different units, so it has to be very well controlled. Okay, one of the disadvantages, the higher level of maintenance. So, and the last thing is the potential discharge of settled sludge during decantation phase, because during decantation phase we are drawing the wastewater from the effluent, and there is no such pumping to the sludge, so the sludge will remain in the tank, and then it will receive another wastewater. Okay, so there is a possibility to discharge of some settled sludge, during the decantation phase, and this is not so good. Okay, now let's see an example here. A completely mixed activated sludge process is used to treat a wastewater flow of 1 million liter per day, and the BOD5 is 200. The mixed liquor suspended solid is 2000. The concentration of the net biomass leaving the system every day is 50. Okay, so this is the X leaving the system. So the aeration tank has a volume of 200. What is the HRT of the wastewater in the aeration tank? What is the average time for which the biomass stays at the system? So let's see here. We have Q node, 1 MLD, 1 million liter per day, which is 1000 meter cubic per day. We have BOD S node, which is 200. We have mixed liquor suspended solids. The X is 2000. The XW is 50, and V is 200 meter cubic. So HRT is V over Q, and this will equal 0.2 days, which is 4.8 hours. And then the mean cell residence time, TC, equals V over Vx. Vx actually is the total biomass present in the system, and QWXU is the net biomass leaving the system. Now, because this is an SBR and all the flow in is converted to flow out, which is there is no such waste, there is no such effluent and underflow waste like the conventional one. So that's why we will consider the Qn equals Q out. Qn equals Q out, because all the flow entering the tank, there is only one tank. All the flow entering the tank would be converted to effluent getting out of the tank. Okay, so Qn equals Q out. So QW will equal Q equals 1 million liter per day. So we can say that TC equals Vx 200 times 2000 over 1000. This is to convert the units. Okay, over 1000 times 50, and we convert the units again. Okay, and so the TC equals 8 days. And that is the end of part 3 and the end also of chapter 7. Thank you for watching the videos, and thank you for following the channel, and I hope to see you in other videos later on in later chapters. Thank you.